I think we have. So before I start today, I thought I should just take stock of. So are there now some special topics which you think should be done in quantum mechanics? Then we can list them and then we can try to.
Sir, I think addition of angular momentum is something I don't know actually. I went to sit for CSIN without studying this topic.
Okay.
So club scoring coefficients and all also.
Yeah, that is the same.
Sir, and also hydrogen atom problems, sir. So.
Okay.
So basically 2D hydrogen atom problem is something that's very interesting, I think. 2D, we usually study a 3D hydrogen atom problem. But when it comes to 2D hydrogen atom problem, it's something unique, I think.
Okay. Any other?
So one doubt regarding another thing, like for research in theoretical physics, do we need a higher rank? Like, do we need? Sir?
Higher?
For research in theoretical physics, do I need a higher rank? Means very low rank, or like I got 95.125.
Yes, sir.
That's good.
No, there is nothing like that.
No, like in SIM.
Yeah,
Okay,
all the other eligibility for getting fellowship.
So actually in like SINP, I saw that for theoretical sciences, theoretical physics, they need CSI rank below 50. And for experimental, they want below 100.
Right.
So like I saw one notification for this year, this time.
Okay.
So like I was just curious that for theoretical parts to research in theoretical physics, like do I need like low rank? That's
This used to, I mean, I see this CSIR giving rank is actually a very recent phenomenon. Earlier, they used to simply say that these many people cleared her CSIR JRF, these many for UGC JRF, and these many for lectureship. They simply used to give numbers. There are no ranks. Now, this ranking is very recent phenomenon in the sense maybe some 4 or 5 years. I don't remember exactly, but at least some 10 years back or 6, 7 years back, I don't think there was any ranking. So, but gate score, they have this ranking, and people used to say, okay, below 100 rank, below this much percentile, and above this much percentile should apply. Now that CSR is also giving ranks, people would like to use it. They would like to put their conditions. So maybe people, those institutes where people would like to join, will set some higher ranks.
so I'm saying that for pursuing research in theoretical physics, like in any institute,
Yes.
like not in SINP, like do I need lower rank to pursue research in theoretical physics?
See, it is not like it is not a general rule, but if you go to institutes like IMSC, for example, only theoretical physics is there, correct? So there they would like to have some good rank for you to enter. Whereas if you take TFR, then they have both theory and experiment. And but generally there is a tendency that theory is tough, so people would like to have slightly better ranks for enrollment into theory.
Okay, sir. Okay, sir.
It's not a rule. Okay. So,
Sir,
yeah.
sir, scattering theory possible? Can you sometime?
Scattering theory is something which I think these students are studying right now already.
Yes, sir.
Maybe towards the end we can try doing it. Because I do not want any interference. So I'm only doing some kind of topics which we have not been studying this semester.
Yes, sir. What method they have studied?
That I think they have not. They supposed to have studied last semester. I guess.
Yes, sir, we didn't study that.
So
That
So Corona has affected that. That we can.
thank you, sir. Thank you.
Okay, so we will. Can I assume that you have done angular momentum theory, and you have, or should I do that quickly and then talk about additional angular momentum?
Sir, it will be great if you could go through it quickly and then go to additional angular momentum.
Okay, so let's start with then angular momentum. So the theory of angular momentum in quantum mechanics is something to do with the starting point is always the commutation relations, because we know that we have this commutation relation between. So I'm going to use this index notation. So I will use my position as x1, x2, x3, and momentum as p1, p2, p. Okay, so that the commutation relation, the basic commutation relation is xi pj is equal to IH cross delta I. Okay, this is the basic commutation relation discovered by Heisenberg, and this is in some sense the starting point. Now, classically, we know that the angular momentum L is a vector defined by R cross P. Okay? So, by definition, you have your, for example, L1 operator is, okay, so I have to say that, okay, x2 p3 minus x3 p. These are the operators. So this is L1 operator. Similarly, you can write down L2 operator and L3 operator. And we can show, and I will not show it here, but I will leave it for you as an show that if you consider an operator Li, okay. So I want you to little bit pay attention that this I is not same as this I. Okay? This I is square root of -1. Okay, so sometimes we can get confused like that. So Li, Lj, okay, is equal to IH cross epsilon ijk Lk. This is Levi-Civita tensor, which I think we have some familiarity with this chronicle symbol and then Lebesgue beta symbol. So this essentially means that it is like if I say this is L1, L2, and this is L3. L2, L1, then this will pick up a minus sign, obviously, because this is a commutator. So equivalently, we can write this, or equivalently, we can write this as a vector. This is a vector operator. It's a vector operator is equal to IH cross same vector operator. Okay, L cross L is IH cross L. This and this mean the same. Normally in vectors, if you say A cross A is 0, but if these are operators, then that is not equal to 0, because an operator is always realized in terms of its action on some particular function, okay, on some particular state, element of the Hilbert space, and so on. And when you do that, you can say that L cross L will be L itself, but for this IH cross. So these two statements are equivalent. This statement and this statement are same, one and the same. Okay, so this is our starting point. So what I'm saying is that you start from commutation of position and linear momentum. Then from there you can derive, or you can show that angular momentum component will satisfy this commutation relation. So this is actually a cyclic commutation relation. That means if you imagine that you have L1 here and L2 and L3. So commutator of L1 and L2 will be L3. L2 and L3 will be L1, but for that IH cross. And L3 and L1 is L2. Okay, and if you reverse the direction, then you will pick up a minus sign. This is the meaning of this cyclic commutation relation. Now we will start with this. Okay, so starting from this statement, okay, starting from commutation relation, we would like to understand the nature of the angular momentum states, quantum states of the angular momentum. Okay, so for that, we will notice that an operator called L square, which is defined as L1 square plus L2 square plus L3 square. So an operator L square can be defined which commutes. This implies that this operator L square commutes with every component of the angular momentum. This here I is 1, 2, 3. Okay, that means there is so essentially, because this commutes with every operator, so I cannot take any component of the angular momentum and then I ask what are the eigenstates, because that there exists another operator which commutes with that. That means, so we must look for common eigenstates of L square and one of the components of the angular momentum, because L square and L1 or L2 or L3, you can, that there is a choice, you can choose, and they form a complete set of compatible observables. So it is customary to work with this set of operators L square and L3 as complete set of compatible observables, and look for common eigenstates of L square and L3. I could have chosen L2 or L1 also equivalently. It is a choice. Okay. Now we would like to understand how these states, what kind of states, and what are the kind of eigenvalues that these common eigenstates have, and so on. So let us say that let a state which I will call it as alpha comma beta be a common eigenstate of L square and L3 such that when L square is operated on this alpha comma beta, we get, so in quantum mechanics what happens is when an operator is operating on some state, the eigenvalue will be of the order of h. When the square of some operator is operating on, you will have h bar square to some alpha, and alpha table the kits with the quantum numbers. So this alpha, so I have one quantum number for L square and another quantum number for L set. Okay, and of course when I have L3 operating on alpha comma beta, since this is only L3, I will have only one H cross, and then the quantum number that comes out. So this is how I am going to define this alpha beta as a common eigenstate with eigenvalue h bar square alpha for L square operator and h bar beta for L3. We don't know what are alpha and beta at this moment. Right now, they are simply some labels. And we would like to get as much information as possible with what these alpha and beta are. So what we can do is we can define, so something similar to what you used to do in harmonic oscillator. So we define two new operators, which I will call it as L plus minus. In terms of, see, among the three components, I have chosen one component L3 in CSCO, and there are other two components. So I will use those other two components to define this L plus minus. So L1 plus minus IL. So if I define this, then so these operators are important. They are not Hermitian operators because you note that note here that you take L plus and then take the adjoint of L plus. You will get L minus. So they are not Hermitian, but they are adjoint of each other. Okay. So the moment we define this, so we can so using this commutation relation, this comma Lj is equal to IH cross epsilon IJK into LK. using this commutation relation, okay, we can show that there are certain results that you can show. Now, the first result that you can show is commutator of L3 with respect to L plus minus. I'm writing this result, two equations in one equation itself, is plus minus H bar L plus minus. That means if you have plus here, it will be plus here. If you have minus here, it will be minus. Okay. Yes.
Can we define this L plus L minus? Suppose if you are working in the common eigenbasis of L square and L1, can we define that?
Yeah.
That case?
Define this state.
So cyclic way we have to choose, or
yeah.
means for L3, L1 plus.
Yeah. So suppose if you are choosing L1, then you define L2 plus minus IL3. See, if you don't choose that way, also there is no problem, because if you don't choose that way, then these commutators, the sign will be different. That's all. But I don't think there will be any problem. You will have a consistent theory. Okay. So, but you will have less trouble if you choose them as a cyclic.
Okay. So this commutation relations will hold good for that case also.
Yes.
But sir, if we see the expression for Lx, Ly, Lz, they are different, right? L3 has a very simple expression in spherical form, like IH plus D by D.
Yeah. So, in fact, the reason why we always choose L3 as a part of CSUO is that because you have a simpler expression in terms of coordinate representation. But at this point, when I'm looking at an algebraic level at this point, I don't know what was the expression, right? And I don't have to bother. Here, all three are on equal footing. Okay. Now, why L3 has a simpler expression and L2 and L1 are having a complicated coordinate expression? That is because of the relation between XYZ and theta phi. Correct?
Yes, sir.
The way XYZ and R theta phi are so related, and that is why their derivatives are so related, and that's the reason why you get a complicated expression for Lx and Ly and a simple expression for Lz. Correct? But that is something which is it is in some sense an artifact of the way we define spherical polar coordinates.
Oh, okay, sir.
We don't have to bother about it at this abstract level. At this level, I don't have any difference. They are on equal footing.
Okay, sir. Yes, sir. Thank you, sir.
Yeah. And then you can also show that if you take, for example, the commutator of L plus L minus. Okay, so you take L plus L minus commutator. Okay, so this will be equal to 2 cross L3. Okay, it's probably easy to, I'm not sure whether minus sign is there or not, but I will leave it for you to show this result. Okay, I don't remember exactly it is L plus L minus or L minus L plus, but that you can figure out. There's only a minus sign that will come if this is not correct. Because you know that L1 and L2 are there in these two expressions, and L1 and L2 commutator is always L3. So L3 will come, that is for sure. But then with a minus sign or plus sign, that you figure out. And of course, a trivial commutation which is easy to visualize is that L square also will commute with L plus minus. Because L plus minus is defined with L1 and L2, so the commutator of L square with them is equal to 0. Okay. So now, so there are two exercises here. This is one show that I want you to just try this on your own. I mean, if you have not done it, you should definitely do it. So this is one show that. So these commutation relations, and then the second one is this. So this is the input for this one, and this is this one. Of relation that is required for you. I mean, in terms of the commutators. So the rule that you will always use is that if you have a operator A and an operator B plus an operator C, this is equal to the commutator of operator A, B plus commutator of operator A, C. Which is also true if you have a sum in the first case. Okay, so this is the first rule. Now the second rule is that if you have an operator A and a product operator B, C, BC, then this is given by A, B, commutator of AB multiplied by the operator C plus B multiplied by the commutator of A. Okay. And the third rule is, suppose if you have a product here, A, B, C, then you have A commutator of B, C plus commutator of A, C into B. Okay. So these three rules you have to use in trying to show these results. So that's the requirement. That's all. So you don't require anything else. Okay. So once you have this, these results, I'm going to assume that these results are true because you can show this anyway. Now we can ask a question, or we start our analysis of what is this alpha comma beta. Now you can see that. So let me define. Okay, so I'm going to, as I told you, I'm going to get as much information as possible about this alpha beta state. So define a positive operator namely L1 square plus L2 square. Because this is a square of a Hermitian operator, this is always a positive operator. What do we mean by positive operator? Positive operator means the expectation value of this operator with any state is always a positive number. Okay. That means, yes.
Should we include 0 as well, like, for positive operator?
No, here I am just saying that it is a positive operator.
Yes, but should we include 0 as the expectation value, like non-negative? I'm saying that expectation.
Yeah, you can. Yes, you can include 0 as a positive, as a what is called. But let me say that, see, it is 0 only if L1 and L2 both of them are 0. Otherwise, it is always a positive operator. Correct?
Yes, sir.
Okay. So this is as such, we will not bother about that 0. It is a positive operator. So this means, so this implies if I take this alpha comma beta and take the expectation value of this L1 square plus L2 square, so this is an operator and this is positive. Okay, so this is positive. Now we can ask a question that but rewrite this positive operator L1 square plus L2 square as L square minus L3 square. By definition, L square is L1 square plus L2 square plus L3 square. Okay, if I write that, that means I have this alpha comma beta L square minus L3 square alpha comma beta is greater than 2. But notice here that this alpha comma beta is an eigenstate of both L3 and L square. So this operator is actually a diagonal. That means this alpha beta is an eigenstate of L square. This alpha beta is also an eigenstate of L3 square. So this implies, so L square operating on alpha beta is h bar square alpha, and L3 square operating on alpha beta is minus h bar square beta square. So this is greater than 2 because alpha beta is a normalized state. So this is an eigenvalue and h square is always positive. So this implies we get a result that this beta square has to be less than alpha. Beta square has to be less than alpha. Okay, so what does that mean? That means that it is like, suppose if beta square is equal to alpha, let's say the beta square is equal to alpha, then you say beta equal to plus minus alpha. That means there is some kind of a bound, both a lower bound as well as an upper bound. So this result tells us that beta is bounded both above and below. Okay, so this bound may be related to alpha. Okay, because beta square cannot be plus minus square root of alpha or something like that. Okay, so if you want to, but I am not going to get any quantitative estimate of these bounds from here. But I just wanted to make a conclusion here, draw a conclusion that beta is bounded. So this is the first information that I try to get from this positive operator. Now the second information, that the second thing that I would like to do is that I would like to ask a question that, or I would like to understand what is the action? What is the action of the operator L plus on alpha comma beta? I would like to know how it acts on that. So for that, let us say that when L plus is acting on alpha comma beta, okay, what happens in general? In general, it will change the state. Okay, so let us call that state as some phi. Okay, so we can call it, say it is some phi. Now we would like to know whether this phi is, so we can ask next question, is phi an eigenstate? Is phi an eigenstate of L square and L3? Okay. Now, is phi an eigenstate of L square? Yes, it is an eigenstate of L square because L square and L plus commute. So I can say that it is an eigenstate of L square, obviously, but it's not so obvious whether it is also an eigenstate of L3 because L3 and L plus do not commute. Correct? L3 and L plus do not commute. So is this an eigenstate of, this is not an eigenstate of L plus, by the way. Okay, so whether this is an eigenstate of L3 is not a trivial question. So we can first ask yes for L square, and this is somewhat obvious. Okay, but we have to investigate for L3. So find if this phi is yes.
Sir, phi is not an eigenstate of L plus. And how you can say that it will be eigenstate
What
of
I'm
L
trying to
square?
say is that we know that L square plus this commutator is 0. Correct? Correct. So now suppose if I ask
sir.
what is L square acting on phi, okay, that is L square L plus acting on alpha comma beta. Correct? Correct. Now since it commutes, this can be written as L plus L square L plus L square acting on alpha comma beta. I am using the commutator here. Correct. But this is an eigenstate of L square, which is equal to h bar square alpha L plus into phi. So this phi is an eigenstate of L square, okay, with the same eigenvalue as that of alpha beta. That is the degeneracy part. Okay, that means this h bar square alpha is an eigenvalue for L square corresponding to alpha beta also and phi also, because L plus and L square commute with each other. Correct? So that is what I said. It is somewhat obvious because if it is commuting, then you can use this this logic to say that that's an eigenstate of this operator also. Okay, is that clear? Okay, so I thought it is obvious, but this obvious the argument for this obvious thing is this one. Okay. Now to find if phi is an eigenstate of L3. Okay. So let us try to operate. Let's try to ask what is L3 acting on phi. That is equal to L3 acting on L plus on alpha comma beta. Now, okay, but then let's go back and ask what is L3 and L plus commutator. Okay, that is what I asked you to show. That is equal to H cross L plus. Okay, so if you can recall that I have plus minus H cross L plus minus, so this is H cross L plus. So this implies, so L3 L plus, okay, minus L plus L3 is equal to H cross L plus. Is the relation. I just expanded this commutator. So now what I have here is this term. Now I can say that this L3 L plus, okay, it's not commuting, but I can write this as L plus L3. I take this to the next to the right hand side, plus H cross L plus. Okay, so I'm going to substitute this. Okay, I'm going to substitute this. Okay, so that is L3 acting on phi can now be written as L plus L3 plus H bar L plus acting on alpha comma beta. That is, I have substituted for this one. Now you see, this is like the two operators. One is L plus and L3 operating on alpha comma beta plus H bar L plus operating on alpha comma beta. I do not know what is L plus operating on alpha comma beta. We called it phi. Beta state is an eigen state of L3. This is H cross beta. So I can write down this is H cross beta into L plus on this one is simply phi plus H cross into phi. Okay, so that is equal to H cross into beta plus 1 into phi. Okay, so what is the conclusion? The conclusion is that phi is also an eigenstate. An eigenstate of L3, but not with the same eigenvalue as alpha comma beta, with eigenvalue H cross beta plus 1. That means whatever was, that means what? Your alpha comma beta, when you operate L3 on this, you get H cross beta into alpha comma beta. But when you operate L3 on L plus operated on alpha comma beta, okay, so when you operate L3 on this, you get H cross beta plus 1 into L plus alpha comma beta. Now what can you understand from here? From here, can we say what is the action of L plus on alpha beta? We can say that action of L plus on alpha comma beta has to be, there should be some constant here, which I will call it as C plus at this moment, into alpha comma beta plus 1. Why did I put alpha here? Because that is an eigenstate of L square straight away with the same eigenvalue. So I don't have to change this alpha, but I have to say beta as beta plus 1 because the eigenvalue is h cross beta plus 1. So this state is actually going to beta plus 1. Okay. And C plus has to be evaluated. But let me tell you that so I will leave it as an exercise. Okay, so this I will leave it as an exercise. You can show that the action of L minus on alpha comma beta is equal to some constant, which I will call it as C minus, into alpha comma beta minus 1. Okay. You can follow the same kind of steps, use the commutation relation between L3 and L minus, then you can get this result. So you please work that out. Okay, so because of this one, these L plus minus, these operators are called raising and lowering operators. Raising or lowering operators. This is exactly same as your A dagger and A in harmonic oscillator. Okay, so
Excuse me, sir.
yes.
Can you explain once more this? How do you come from this L3, L plus, this last two steps? How you come from this to this L plus alpha comma beta is equal to C plus?
So if you look at this one, this is definition of alpha beta, correct?
Okay.
H cross beta is the eigenvalue. Now from this analysis, we have asked what is the is phi an eigenvalue? Then we have obtained an answer saying that yes, phi is an eigenvalue of L3, eigen state of L3 with the eigenvalue h cross into beta plus 1. Correct? But this is your phi.
Yes.
Whatever I have written here, this is your phi, right?
Yes.
So if L3 is acting on phi, it is an eigenstate of L3 with an eigenvalue h cross beta. That means the state itself should be labeled with alpha and beta plus 1. Only then it will be consistent with this definition, right? So whatever is beta sitting here, that beta is coming here. So if beta plus 1 is there, then in this phi it should be like beta plus 1. Correct?
Yes.
Like that.
Thank you, sir.
Yeah. So these are called raising and lowering operators, or sometimes they call them as ladder operators. Okay. Fine. Now we have to, of course, find out what is C plus and C minus, but let's come back to that a little later. Okay, so just remember here that we have to determine C plus minus. Okay, so this we have to determine because these constants are also important. So we will come back to this later. Okay, so this is about action of, okay, so maybe the question that I asked earlier, I can generally ask because I have done one part and I have left it for you to do the other part. So let me ask at this point, what is the action of L is the action of L plus minus on alpha comma beta. So first we start with L plus. Okay, let us look at L plus. And then we did this for L plus, and I asked you to do it for L minus. So this result is something which we have now. So L plus will actually raise this quantum number beta, and L minus will lower this quantum number. Alpha remains the same. But notice that since beta is bounded above, okay, there will be some largest value of beta above which there is nothing, correct? So since beta has an upper bound, and this is what we have seen in our with respect to our positive operator. Since beta has an upper bound, call it some beta max. Okay, beta max. We have the following. We have what happens when you take L plus and then try to operate it on alpha comma beta max. It should be beta max plus 1, but then beta max is the upper bound, so I must define that such a thing should be 0 because there is no state beyond beta max. Okay, so I am going to define my beta max such that when L plus is operating on that, it is equal to 0. Correct? So it cannot raise further. That it can only raise up to beta max. And if you reach the ceiling, then that's all. That means that state, this L plus should kill that state. Okay, so that means, so this is like yes.
Sir,
Yeah.
sir, can we say that this alpha beta max is an eigenstate of L plus?
No, alpha beta max is not an eigenstate of L plus, but that the action of this L plus and alpha beta max is 0.
Yes. Okay.
So now you can ask a question that suppose if I take this left hand side, okay, and then take an inner product of itself, because this is 0, its inner product will also be 0, correct? So that means if you take alpha beta max and inner product, when I take, I will have to take an adjoint. When I take adjoint, L plus adjoint will be L minus, and this is L plus and alpha beta max. This should be equal to 0. Okay. So, but notice what is your L plus and L minus? L minus into L plus is essentially L1 minus IL2 multiplied by L1 plus IL2. So that is equal to, you have L1 square, L2 square, and you have plus I times, so L1 L2 minus L2 L1. That means you have L1 comma L2 commutator. Correct? So that is equal to, I can write this as L square minus L3 square. And what is commutator of L1 L2 is IH cross L3. So I and I will become minus 1. So minus H cross L2. So this L minus L plus is an operator like this. So that will tell us that this alpha, so thus we have alpha beta max L square minus L3 square minus H bar L3. This is the operator alpha beta. Now this is equal to 0. But now you see that all these operators that are there in this combination, these eigenstates, these states are eigenstates of all those operators. So that means I can get it is like H bar square into alpha minus H bar square into beta max square minus H bar square into beta max. That is equal to 0. Okay, so that is equal to 0. Okay, so that implies we get a relation that alpha is equal to beta max into beta max plus 1. So this alpha should be equal to beta max into beta max. Okay, so this is what we have with respect to the upper bound. Okay, now we can ask a similar question and do a similar analysis with respect to lower bound. Okay, so we ask a question since beta has so let beta min be the lower bound on beta such that L minus acting on alpha comma beta min is equal to 0. L minus acting on alpha beta min is equal to 0. Now this means, once again I do this trick of taking a inner product. I have alpha beta min into the adjoint of L minus is L plus. So L plus L minus into alpha beta is equal to 0. Now what should be your L plus and L minus? L plus and L minus, as you can see that only there will be a minus sign in this particular case. Okay, so that is you have L1 plus IL2 into L1 minus IL2, so which is equal to L1 square plus L2 square minus, because L1 L2 is a minus, so there's a I L1 comma L2. So that becomes so this will be equal to L square minus L3 square, and you will have plus H cross L. Okay, so you can substitute that one, and then you have alpha beta min into I have L square minus L3 square plus H cross L3 alpha beta min. This is equal to 0. This implies you have H bar square alpha minus H bar square beta square beta square plus H bar square beta min is equal to 0. This implies we have alpha is equal to beta min into beta min minus 1. So this is what is alpha as far as this lower bound is concerned. Now we have these two relations. Both of them are, of course, we do not know what is beta min and beta max, but both of them are related to alpha in terms of these equations. So this implies we can now try to determine at least a relation between beta min and beta max. So this implies we can say that we can now write that beta max into beta max plus 1 should be equal to beta min into beta min plus 1. Okay, so this implies that you have beta max square. Okay, so I have a beta min square, so I take it everything on this side. So beta min square plus beta max, and I have plus beta min is equal to 0. Okay, so I can write this beta max square minus beta min square in the following way. I have beta max plus beta min. Okay, this part I can take it out as a common. Then I have beta max minus beta min from this equation. Okay, and plus 1 is equal to 0. Okay, so there are two solutions for this. One solution is that beta min is equal to minus beta max. That is one solution. And the other solution is that beta min is equal to beta max plus 1. So mathematically, even though you have two solutions, but beta max is the maximum value that you can have. So beta max plus 1 cannot be beta min. So this is an absurd solution, so we don't have to bother about this. But this is the solution which makes sense. So beta min minus beta max, beta min is equal to minus of beta max. Okay, so the relation between beta min and beta max is that, so the relation so we have beta min is equal to minus beta. Now let us argue something like this. That is, start with alpha comma beta max. Okay. Now ask what is L minus acting on alpha comma beta max. Then you will get some constant. So let's say this is proportional to alpha comma beta max minus 1. Okay. Then you again try to operate L minus on this. That means you take L minus square on alpha into beta max. Then that will be proportional to alpha beta max minus 2. Now you go on doing this up to some n. Okay, so many times, such that alpha beta max, when you operate this many times, it is going to be alpha beta min. Okay, because every time it is changing or lowering by 1, I can start from beta max and come to beta min. Correct. In fact, this n is n is an integer, right? So we can say that beta max minus beta max can be written as is beta min plus some n. This n is some integer, some positive integer. But we know that that this beta min is equal to minus beta max. So if I substitute that, then what happens? I get a minus beta max here. I take it to the other side. I get 2 times beta max. 2 times beta max is equal to n. Or your beta max can be n by 2. Beta max can be n by 2. And you simply call this n by 2 L. Okay? You can call this beta max as L. So, what is it that we are finding here at the end is that we can say that there is, so we are, and what are the values that L can take? Okay, yeah, so n is an integer, so if n is equal to 0, this is 0, if n is equal to 1, this is 1 by 2. So we have L which can take values 0, 1 by 2, 1, 3 by 2, etc. That is, it can take values integers or half integer. Okay. So now we can summarize the findings. Okay, so to summarize, we can now simply call this state. So let us label the state. To be some L comma M. So the largest value that M can take is plus L, and the smallest value that M can take is minus L. Okay, we can call this as okay. Now, in terms of this beta max, okay, in terms of this beta max, which I called it as L, what is alpha? Alpha equal to beta max into beta max plus 1. So, such that my L square operating on this Lm is equal to h bar square into alpha, but alpha is now L into L plus 1. L into L plus 1 into L comma. And L3 acting on M. Lm are eigenstates that are common to both L square and L3. H bar M into Lm. Okay. So this is the conclusion that we have with respect to this. And of course, I have said that this particular value L can take 0 any of these integrals, and once for a fixed L, for a given L, M can take values from minus L to plus L. So this is the completion of the story. Okay, but there is an interesting question, an important question also, namely, as Shrikant was pointing out in the beginning, that suppose if you did not do this problem in this fashion, suppose if you have done this problem by writing down the differential operators in terms of spherical polar coordinates. Okay, so if we solve this problem, in coordinate basis, then you have this L square operator has got this kind of a thing, that this is equal to 1 by sine theta, rho by del theta into sine theta, rho by del theta, plus 1 by sine square theta, rho square by del phi square. So you have an expression like this. This comes from the Laplacian of spherical polar coordinates. And then, of course, your L3 operator is minus IH cross rho by del phi. So if you use them and then ask for what are the common eigenstates of these two things, then the eigenfunctions, the common eigenfunctions, of L square and L3 are essentially the spherical harmonics, YLM theta gamma phi, such that when L square is operating on YLM theta phi, these are normalized eigenstate of L square and Lz. You will have H square L into L plus 1 YLM theta phi, and when L3 is acting on YLM theta phi, you have H bar M acting on H bar M into YLM theta phi. So essentially, in terms of the notation that we have learned, so if you take this state Lm and then ask what is its coordinate projection, then you will have this as your spherical harmonics, YLM theta. This is okay, but there is a problem here. The problem is that if you have solved this problem in this fashion, allowed values of L are simply 0, 1, 2, 3, etc. Only integers. Only integers. There are no half integers. Okay, so no half integers. Okay, so if you solve this angular momentum problem in coordinate basis, you get perfectly common eigenstates, whereas the value of the quantum number associated with the angular momentum can take only integer values. Now, if you do an algebraic method, you start from the commutation relations, then you seem to be getting getting a result where this L actually has both integers as well as half integers. So there is a discrepancy to this extent. Okay, so now I do not know if you have realized this or if you have done this in this particular fashion any time. So is there any answer why this discrepancy is there? Yes.
Is it because that here YLM we have a constant that if we change phi to phi plus 2 pi, and the state remains same?
Even that single valuedness.
Yes, sir. Single valuedness.
Basically, single valuedness does not limit this to be integers. Okay, so for example, so suppose if you want to just ask that question, so what you are asking is this restriction of L to integers a consequence of single valuedness of psi of r theta phi. So that is the question that you are asking. So yeah, so so for that, suppose if you take one particular common eigenstate of L square Lz and L3, L square L3 and okay, I don't have to bother about R here, but anyway, let us write, if there is some kind of a radial part also, let us write it like this. But if you take two, suppose let's say that let's say two states, okay. Suppose if I take two states, okay. So consider a linear combination of two eigenstates of L3. Okay, phi is equal to some kind of a let's say A of r theta. This function, whatever it is, it doesn't matter. But the eigenstates of L3 are going to be like e to the im phi. And then there can be another function B of r theta into e to the power im prime phi. So m and m prime are different. Now we demand that single valuedness means that psi of r theta phi plus 2 pi should be same as psi of r theta phi. Okay. Whenever we say this is equal, this is always up to an overall phase, up to a global phase. Okay. So suppose if you ask now, what is this psi of r theta phi plus 2 pi? That is equal to A of r theta into e to the power I m phi into e to the power I m 2 pi. Okay, I do not know what is m at this moment. I am not saying it is an integer. B of r comma theta into e to the power I m prime phi into e to the power I m prime 2 pi. So this I can pull out e to the I m 2 prime. So let's say I write e to the power I m prime 2 pi into a of r comma theta into e to the power I m phi into e to the power I m minus m prime into 2 pi in plus b into e to the power I m prime phi. Now this is a global phase. Okay, this is a global phase. So that doesn't matter because we can only say up to a global phase. So we can ignore that. But this factor, okay, should be equal to 1. This should be equal to 1. If single valuedness means that we should have so we should have e to the power I m minus m prime into 2 pi should be equal to 1 for single valuedness. Okay, so that means we should have when will this be possible? When your m minus m prime is an integer, okay, is n some integer. Only then it is possible, right? Okay, now there are two possibilities. Possibility one is that this is an odd integer. Okay, if n is an odd integer, then your m and m prime have to be integers. Correct? M and m prime have, this implies m and m prime are integers. The other possibility is that it can be an even integer. That means now I can say this m minus m prime is equal to some 2 times n prime. Okay, 2 times n prime. Okay, so that means this n prime is an integer. Okay, so n prime is integer. Okay, so that means I can have m by 2 minus m prime by 2, which is equal to n prime. Okay, so I can have this half integers. Okay, so this m and m prime can be half integers as well. Then also you see to that m minus m prime into 2 pi is equal to 1. So what is that we are saying here is that if you demand single valuedness, that tells you that your m and m prime or whatever m value can be either integers or half integers. It is exactly like what we have shown through our algebraic method. Okay, so we are getting kind of a consistent result. So single valuedness is not going to have this restriction because it can be integers or it can be half integers. Okay, so this is as far as single valuedness thing is concerned. So this question, that is this restriction L integers to single valuedness, the answer is no, because there is no restriction if you have single valuedness.
Sir?
Yes.
So I think for spin we can use the half integers. Like for orbital angular momentum we use only integers, values are well. But for spin we have half integral values of like spin angular momentum.
That is exactly correct. But what I'm saying is in my analysis I have not included spin anywhere. Right. So when I started with this angular momentum, I have only started with this commutation relations, which are satisfied by the orbital angular momentum also. So I started with commutation relations, and then I simply at how this eigenstates can be defined, and then I found by using this raising and lowering operators, the conclusion I have drawn finally is that this L, which is a quantum number associated with the angular momentum, can have integers and half integers. Whereas we know that if you have only orbital angular momentum, there cannot be half integers. Only if you have spin, then only half integers can be there.
Sir,
Yes.
but for spin, we cannot write a differential equation like in coordinate basis, right? For angular
Correct.
momentum only we start with x and p.
Correct. Correct.
So this L3, sir, we can write in Schrödinger representation like difference of two harmonic oscillator Hamiltonian.
Okay. So essentially, what you have to understand is that if we have this angular momentum operators, because angular momentum operator is defined from R and P. Okay, so the angular momentum has got certain commutation relations with the coordinate as well as the momentum, whereas spin does not have any such relation to x and p. Okay, so if we use those commutation relations of L x y z and L p x p y p z, they should somehow restrict this the allowed values of L. Okay, this is what is supposed to be called as Schwinger's oscillator representation or Schwinger's oscillator model. So what you do here is that you write down your L3. Okay, so you write down your L3 as Q1 P2 minus Q2 P1. Okay, I think I was writing it as XP, right? So this is X1 P2 minus X2 P1. This is my L3 operator. Correct. Now I can define some quantities. For example, let's see. Let me define a quantity called Q1, which is given by X1 P2 by root 2, and Q2 is equal to X1 minus P2 by root 2, and P1. Okay, so maybe I should write them as capital Q1, Q2, and then capital P1 as P1 minus X2 by root 2, and capital P2 as P1 plus X2 by root 2. Okay, so if I define like this, then I can write down, so write X1, X2, P1, P2 in terms of, okay, so these quantities in terms of capital Q1, capital Q2, capital P1, and capital P2. You can write this by inverting this. Okay, so you can write these relations and substitute them here. Okay, and substitute in L3. Then I will not do this algebra, I will leave it for you. Then we get L3 to be equal to half Q1 square plus P1 square minus half Q2 square plus P2 square. Okay. Not only this, and importantly, you get the commutation relation between Qi comma Pj to be equal to IH cross delta I. That means these are like position and momentum operators because their commutation relation is like this. Now, if these are like position and momentum, then this is like harmonic oscillator, correct? This is like harmonic oscillator, one harmonic oscillator, two different harmonic oscillators. So, in terms of the quantum numbers, so the quantum number associated with L3, okay, so is equal to M. Okay, this is for L3, and the quantum number associated with this particular operator is some n plus half. Okay, forget about h cross omega, etc., because all this omega, everything is equal to 1 in this thing. And then this one is like some other quantum number n prime plus half. So it looks like this n and n prime are integers, by the way. So this is n minus n prime. So this is the difference between two integers. So you cannot have difference between two integers as a half integer, and hence this this structure of difference between two oscillators for the L3 operator is only because of the relation that it has with respect to position momentum operator. So this tells you that M cannot be half integer. Okay, so this is the argument to say that even though algebraically you are getting an expression that it can be integers or half integers, but orbital angular momentum must also satisfy a structure which because of its relation to coordinates and momentum operators, which can be cast as if this L3 can be written as a difference between two harmonic oscillators. Because of that, your M cannot have half integers. So that is the resolution of the question. So this is the nature of the theory of angular momentum, and so if there are questions, we can take up, because I think I will not be able to do justice if I start addition of angular momentum now, but we will do it in the next class. The addition of angular momentum and Clebsch-Gordon coefficients, we can do it in the next. So any questions?
Sir, I have a small doubt. Sir, why is the global phase called so? I mean, why is it named so?
Its names basically global phase means it is an overall phase. Okay, in quantum mechanics, so what happens is that if you have a state, let's say you have a state psi, and then a state e to the power some I theta into psi. Okay. Now in quantum mechanics, these two represents the same physics. Okay, so give same physics. Why? Because the physics is always obtained by calculating probabilities and expectations, which will involve psi star psi. So when you take psi star psi, this I e power I theta will cancel. So in quantum mechanics, this is a very important thing to remember. In quantum mechanics, state is described up to an overall overall phase. The state can be described in overall phase. That means psi and e power I theta into psi is SL. I want to just give you some simple illustration of this. We did a problem like this earlier. That is, you have an infinite potential well and then a finite potential well here. Then we said when we have a ground state, the ground state looked something like this. It doesn't go to zero; it goes like this, and then it just exponentially decays. Correct? The wave function has to be continuous at this point. It exponentially decays. This is the ground state wave function that we talked about. Suppose if you are asking what happens to the first excited state, okay? So let's say you are talking about first excited state. There is going to be a node for the first excited state. That means it's going to go down like this and then come up like this. Going to go down like this and come up like this. Now, the wave function, if you want to understand how this wave function will be now continuous, because this has to go down, right? In the sense, you have to have somewhere here, and then this wave function has to come like this. Correct? I think I'm not drawing it very clear picture, so let me try it again. Okay, so let's say we have a particle in a box. So the ground state is something like this, and the first excited state is something like this. Correct? So now if you say that I am going to reduce this to a finite level, then the ground state is going to be something like this, and then it just decays like this. And what will happen to the first excited state? That's the question that I'm asking. So you see that this first excited state will be something like this. Okay, it will not be, but then what will happen to this wave function here? The wave function, whatever is the value here, this minus value, you have to take the plus value here, and from there the wave function will be. Why? Because the wave function, you multiply with a negative sign, or you, instead of taking this one, you take the minus of this wave function. That means it will be something like this, and then it will go up to this, then it will go like this. So when you take minus of this wave function, then it will exactly match at the boundary. Take this wave function, it appears that there is a discontinuity at this point, but there is no discontinuity because psi and minus psi represent same physical state. Okay, so that is what we say that. So why do we call it? So the next question is, why do we call it global? So there are two kinds of nomenclature. One is called a global phase, other is called a local relative phase. That is because suppose if I have psi, which can be written as some phi 1, some c1 phi 1 plus c2 phi 2, phi 2 plus c3 phi 3, like that, then I can have an overall phase. Overall phase means this whole thing is multiplied with some e power I theta. This is a phase for this, for this, for this, and that is of no use. That is why we call it as a global phase. I can have a situation, maybe there is another state psi prime, which is equal to c1 phi 1 into e power I theta 1 plus c2 phi 2 into e power I theta 2 plus c3 phi 3. Okay. Now this is not an overall phase. This is a relative phase, because this phase is only for this particular state, and this phase is for this particular state. So this cannot be ignored. The relative phases cannot be ignored, but overall phases are unimportant. So that is the language.
Yes, sir. It is very clear, sir. Thank you, sir.
Sir.
Yeah.
Sir, is this phase is a measurable quantity in quantum means? Can you measure this phase in quantum mechanics?
Yes, you can measure. Relative phases can be measured. You can do you can do interference measurements to measure these relative phases.
Yes, but global phase, sir. Global.
No, global phase is not. Global phase is it's not physical. That is, we don't have any way of physically getting some information about that.
Yes, sir. Sir, this time in CSIR, the comparison of ground state energy of infinite square wave, semi-infinite, and finite square wave, their ground state energy comparison. Just.
I have seen that paper. Yeah, I think that. So maybe I think Debanjan was asking a question in the chat box in the beginning. Shitikanta, you are the right person probably to make a guess. What could be like a cutoff? I must tell you that Shitikanta has cleared CSR when the cutoff was very high. What was the cutoff when you cleared, Shitikanta?
Sir, some 108, I think.
108.
My score was some 125.
Yeah. So even if it was a little more, you would have cleared it. But since you have seen the paper, do you have any guess what could be the cutoff this time?
Yes, sir. I think, sir, 75 to 80 for LS, I think, sir.
So I made a guess when Debanjan asked 90 probably for the other.
Yes, sir. 90, I think, sir, safe for JRF, general category 90.
Sir, if I get 95.125, will I get like research in theoretical physics? Like, can I pursue research in theoretical physics? That's.
Yeah. I think. See, there are some institute, as you pointed out in the beginning, which are asking for some rank-based upper cutoff, but there are many institutes who don't ask this. For example, I think IASC don't ask any cutoff like that. IASC will ask you to apply, and then they will conduct an interview, and based on the interview.
Okay, sir. So can you would you prepare us for interviews? Like, that would be helpful.
Yeah, we can do that. Online interviews nowadays, I don't know how they are going on, but I hope we will be able to meet soon. I'm hoping this for a long time because interviews always. Johnson, what are you saying?
Sir, I was asking, is the campus going to reopen soon?
I wish to see in Tamil Nadu, they have said that they are opening for final year students, at least all colleges and universities. I don't know if they have opened, but they are supposed to open from at least final year should come, otherwise you will lose all your college time.
That is correct, sir.
First year,
sir, even if it opens for the evening classes, please continue, sir. Evening classes, please continue.
Yeah. So maybe these some of these things, I don't know. Some people are probably thinking that this is doing well, so let us continue like that. Because there is a lot of saving, no? A lot of electricity saving and institutes are saving money. Shruti, you said something? Did you say something, Shruti, about they opened, right? Yeah, that's what I heard. In Tamil Nadu, they have opened. There, somewhere I saw that they're doing temperature testing and then allowing students to come in. I think you should also demand. You want to come. Probably you should write.
Actually, people are getting somewhat restless to be back on this.
Same thing you are doing in your home also. It's that, are you simply sitting at home? Probably you are going
No.
out and then moving around. So same thing you can
Yes,
do.
sir.
Take care of yourself. And see, you are not school students, no? You can take care of yourself. I think it should be fine. University students can come. See, when,
Maybe it will happen soon.
see, I found during Diwali time, all shopping was completely crowded. There was no social distancing and there was jam packed. Close packing was there, no social distancing. So I think somebody said that in some shops there was no place for Corona to enter because it was so packed.
So it is also somewhat similar here, but people are having masks and many people are keeping it below their nose. So that's all. There is no difference in the any situation.
It is just for okay, I also have mask.
Sir, okay, sir, will you...
Anand Kumar Tiwari, how are you?
Yes, I am fine. Yes, sir.
Are you able to come out of Delhi?
Yes, sir. I'll come if university will be open.
No. Now I think all routes are closed. No, there is a lot of protests.
But sir, it's like I'm not follow direct. Like I'll come to some other
You
place.
can take a flight.
Some bus, then I come outside. Then
You can take a flight.
yes. Last time I came this flight, so maybe I'll take flight.
Yeah. Debanjan, you said something.
Sir, will you prepare us for interviews after this? Sir? That's why I asked.
Yeah. We can discuss. We can discuss some possible interview questions.
So on what basis candidates are evaluated, sir? Like on their knowledge only?
Yeah. So interviews are mainly to test how much you have understood, what you claim you have understood. So you can safely make your claims. Okay, if you claim that you have understood quantum mechanics, they would like to test quantum mechanics. That's the generally trend of any good interview.
You don't need to study everything. Like I have to study one or two things very well.
Yes. And if you have a preference, like for example, you want to work in some area, let's say you want to work in high energy physics, then you should know quantum mechanics, some quantum field theory, some basics of particle physics, nuclear physics. So, because you should not say that, okay, I want to work in high energy physics and then say that I only know electronics or I only know spectroscopy, like that you should not say. So some related areas you should choose if you have chosen your area. If you are not chosen your area, you are open, then you can say, I am open to anything, but I have prepared these subjects. So you please ask me questions from these subjects, like that you can.
So we have to apply to a faculty who has a specialization. So I have to look at a specialization and read about that.
Generally, it is like if you have already made up your mind that I want to work in this area, I want to work in this field, then you have to do that. But suppose, let's say that you want to, let's say I want to go to TF or I want to go to IAC, like that if you have, then you are now not fixing your area, you are ready to work in any area, but you want to work in ISC or you want to work in KFR like that. Then you have a choice. You can prepare anything you want, and whatever you get, you will work like that.
So I have to, like, my preference is theoretical physics, but not very specific. Like,
Yeah. So that means you still have a lot of room, no? So, okay, I want to work in theoretical physics, and so basically, you should not say that you should not fail to answer some questions in quantum mechanics, mathematical physics. Okay, then they'll say, okay, then how can you work in theoretical physics? Like that, they may say. So if you want to do theoretical physics, then prepare well some of these theory courses like quantum mechanics or electrodynamics, mathematical physics, these courses.
okay, sir. And do they ask only from basics?
Yes, most of the questions, 90% of the questions are from basics. In fact, I used to always suggest when students go to interviews, read only first 2 chapters of every book. They'll always
Okay, sir.
ask
Okay, sir.
this.
Thanks.
Sir,
Yeah.
sir, can we call computational physics theoretical physics or experimental physics?
As of now, colloquially, it is called theoretical physics only. Anything that is not an experiment is called theoretical physics.
But we are actually conducting all experiments only there.
Correct. But that's what nowadays there is a tendency to call that as a third category. It is not. It is neither experiment nor theory. So you can say I do experiment, I do theory, I do computation. So it is emerging as a third discipline almost.
Sir, last time, sometime earlier, you were saying that you were working on quantum information problems. So, sir, what is exactly, sir? What is the problem that you're doing currently?
Probably at 10 o'clock, I think we should not open up that topic now.
But you can still give us a small outline.
So essentially, what we are looking at is we are trying to understand. I am trying to understand basically the structure of quantum mechanical space and the states of composite systems. That means 2 or 3 systems when you put them together, and look at how these correlations from one state to the other state, which are only quantum mechanical in origin, will help us to communicate some kind of information from one system to the other system. One of the very important protocol that many of you might have heard is something called teleportation. You can communicate the information about the state of the system to a very distant system by simply not transferring anything physically. There is no physical transfer of anything, but the information can be transferred. And that can be done because of the correlations that are already there among the systems, which are called non-local, non-classical correlations. Entanglement is one such correlation. So based on these correlations, we will be able to transfer some information. And this information transfer is very special to quantum features because entanglement is involved there. And so we try to ask a question that how effectively can you do this, or what is the success rate, and how to, suppose if there is an environment which is degrading this one, how to minimize such degradation. So these are the questions that we ask and try to answer.
So is it a computational problem or is it a theoretical physics problem?
This is actually some computation one can do, but largely this is a theoretical problem. See, it is doing computation it is not a simulation like thing. See, when you are doing some simulations, no, like molecular dynamics or Monte Carlo, this kind of simulations, then you are actually trying to mimic the actual dynamics of the system on a computer. This is not like that. This computation. That means we are just using. It is like using a calculator to do some calculation. You are using this computer to do some calculations. That's all. That much is the usage of computer.
What about this quantum computing?
Yeah, quantum computing is also a similar. I mean, basically, it is this. It is a part of this area. Quantum information is a general word. So, quantum computation refers to using this quantum mechanical structure of the states in terms of getting some intrinsic parallelism, and also the quantum mechanical information can be stored in different members of the wave function in a superposed state, and you can use that to do certain tasks which can be done by classical computing only in an exponential time. If you use quantum computation, you can do them very fast. But the important point is that quantum computation is not yet scalable. That means you can now demonstrate with some small proof of the concept like experiments, but experimental scalability is still not achieved. So that means for quantum computation to become practical, that kind of technological advancement has to come.
Many institutions are currently offering this courses on this quantum computing and all. So I was just for the sake of exposure, I was just going through the. So and they were.
Yeah, it is good to take a course on this, because I think there is a lot of future for this field, and there is definitely there is a lot of scope for improvement in terms of avenues. Also, I think a lot of institutes who are starting research in this area.
I actually find it a little bit interesting than many of the fields. So
yeah.
Okay, sir.
Okay, Ashlyn, we will close.
Yes, sir. Good night, sir.
Good night.
Good night, sir.
Thank you, sir. Good night.
Good night.